Let's continue looking at the rotational kinematics. So here is a list of the results that we arrived to in our previous video. Now the most important thing is that you see how we can go from linear kinematics to rotational kinematics using the formulas S equals R theta for displacement, V equals R omega for speed and angular speed, and A and R alpha to go between linear acceleration and angular acceleration. Using those, we're able to arrive to two very useful kinematics equations. Now, we're going to extend that, and we're going to find that the average linear velocity has a similar relationship to the average angular velocity, meaning it's the average between the initial and the final quantities. The displacement x equals x0 plus v0 t then becomes theta f is equal to theta 0 plus omega t, where here omega and v are our average quantities. V is equal to v0 plus at. Similarly, we have omega equals omega 0 plus alpha t. Now, what we're going to spend some more time on is exploring the relationships between linear force and linear momentum, and torque and angular momentum. Now, you know that when m is constant, the formula d dt of momentum simplifies to ma, because the mass doesn't vary with time, so it can be taken out of the derivative operator. Similarly, we're going to have that torque is equal to I alpha when I is constant. I is the moment of inertia, and it is defined as mr squared. We are going to show that. Finally, we're going to be able to find an expression for kinetic energy and an expression for a rotational kinetic energy, which is going to be equal to 1/2 I omega squared. And there you see the analogous quantities I and m, v and omega. All right, so what about torque? Well, torque is normally defined as R cross F, which can be simplified as R perpendicular F, meaning is the portion of R that is perpendicular to the force. Similarly, it could be the portion of the force that is perpendicular to R. Now, in circular motion, you notice that R is always perpendicular to the trajectory. So, R and that linear force, F, are always perpendicular in circular motion. So, torque equals Rf results in R times ma, which is our force ma, and that is equal to mr squared alpha. Now here we're really only considering a single particle, but we would like to consider a collection of particles, since a rotating object could be an object, and that object is made up of many particles held together by some force or because it's a solid. So the total force is equal to the sum of the forces. Similarly, the total torque is equal to the sum of the torques of each individual mass. So that becomes, instead of being mr squared alpha for one mass, it's mi times ri squared times alpha I, meaning the mass of the ith particle times the square of the distance r to that ith particle times the angular acceleration of that ith particle. Now we can simplify this by defining that quantity I as the summation of m times r squared for each of all the particles that we're considering. So I is equal to the summation of mi ri squared. And that lets us have a very simple form for torque, which is equal to I alpha. Now, what about momentum? So you may recall that we had a definition for force that said that force is equal to the time derivative of momentum, to the rate of change of momentum with respect to time. So similarly, we may be able to come up with an expression that says something like torque is equal to the rate of change of angular momentum with respect to time. But we will have to find what that L really means. But we do know that torque is equal to I alpha because we just derived that. So whatever L is has to be such that when we look at its rate of change with respect to time, when we take its time derivative, it has to give us I alpha. So then the L dt has to be equal to I d omega dt. Again, here I made the simplification, the assumption that I is constant, just like mass is constant when we arrive to F equals ma. And so therefore I was able to take the derivative outside, take I outside the derivative. And I can see that I would be constant, and then dl dt would simply be something along the lines of d omega dt. That means that that quantity L that we were looking for would have to be I omega. And indeed, if you take the time derivative of I omega, you would get I alpha so long as I is constant, meaning the mass is not changing or the mass configuration is not changing, which is what the moment of inertia really gives us an idea of. Now, what about energy? Well, we have arrived now to our similar quantities for m in the linear case and I for the rotational case. So if we have Ke, kinetic energy, equals to 1/2 mv squared, we would have some other quantity related to the energy of rotation, which is not the same energy, but is an energy. That is rotational kinetic energy, which is equal to 1/2 I omega squared. Again, this kinetic energy is the kinetic energy that is related to the rotation of an object, not the kinetic energy that is related to the linear movement of an object. And with this, we have concluded the relationships between our linear kinematics and our rotational kinematics.